So suppose I take a flat plate, okay. So I said there is going to be a boundary layer. So let us look at the momentum boundary layer. So this has been dealt with quite extensively in your fluid mechanics course. So I will just briefly outline and will not go into the details of explaining all aspects of the momentum boundary layer. So what happens is that the fluid which is coming past this object, so let us say the free stream velocity is u infinity, okay. So suddenly at y equal to 0 and x equal to 0, the fluid will suddenly come to rest at this location here, okay. So but because of continuity, so note that it is a continuous stream, okay. So the fluid which has come to rest here, it is now going to retard the fluid particles which is actually flowing above it. Supposing we take a fluid particle here, okay. So that fluid particle, before it is felt by the flat plate, it is moving at a velocity of u infinity. But then as soon as it sees the flat plate, the fluid particles below it has come to rest. So now because of continuity, it is going to retard the fluid particles which is actually placed above it. So therefore, you are going to see a temperature gradient and velocity gradient and velocity profile in the boundary layer, okay. So this is the boundary layer. So therefore, du, if u is the x component velocity, so du by dy is not equal to 0, okay. So before the plate, so for y less than 0, du by dy is 0, okay. This is very important because we assume that it is a flat velocity profile, and so the velocity of every fluid particle is actually exactly the same, and so there is no gradient in the y direction. But as soon as it sees the flat plate, now suddenly there is going to be a gradient in the y direction. Why does? Oh, I am sorry, thank you very much. X less than 0, that is right. So for x less than 0, there is going to be a gradient of the x component velocity in the y direction, 0 gradient, but when x is greater than 0, there is going to be a finite gradient, okay. And that is because the fluid particles which is at the surface, they have come to rest, and because of continuity, they retard the fluid particles above it, okay. Fluid is not, that is true, it has a viscous shear. We are going to talk about shear stress very soon, but note that it has viscous effects. Now what happens is that because of viscous effects, you will see that the gradient is going to come in both directions, and in fact the retardation, why does it retard? Because there is a definite viscosity, and so when there is one fluid particle which is at rest, the other fluid particle is now trying to flow at a certain velocity, but then it is going to offer a retardation because of the viscosity, right. So but if it is not continuous, right, if you assume the fluid to be non-viscous, but is there a fluid which is not viscous? It doesn't make sense, because at the boundary, viscous forces are the ones which play dominant role, even if the viscosity is very small. No, at the interface, excuse me. Why? In the boundary layer it is not viscous forces?
Viscous forces are supposed to be with respect to the saline side of the molecule.
Yeah, so supposing I take a section here,
Not there, down.
here it is 0.
That's what?
At the boundary, at the interface it is 0, but we are talking about retardation in the boundary layer, right. So we are talking about the element which is present here. I mean, it could be here, this element could in principle be very close to the surface, it does not matter. Only that monolayer of that fluid particle which is in touch with the surface has 0 velocity, and because the velocity is different, the viscosity is now going to, viscous forces are going to retard the fluid from flowing in the same velocity above it. The velocity cannot be the same because the viscous forces are playing a role, but if there is no continuity, then that's not going to propagate up to the boundary layer. So because the fluid stream is continuous, that's why the gradient is propagating all the way up to the boundary layer, otherwise it's not going to propagate. So continuity is an important assumption here. If the system is not continuous, then everything is going to crash right at the monolayer. So it's very important, continuity plays an important role here. And because of this gradient, you're also going to have a gradient in the x direction, right, because of the continuity equation. We're going to see that in a short while. Okay. So now this thickness is what is called the boundary layer thickness, and this is obviously a function of position. This is obviously a function of position, and so the boundary layer thickness is defined. So note that it's a definition. So boundary layer thickness, okay, is defined as so the location where boundary layer thickness is defined as that location where the u of y, u at delta x, so delta is the height of the boundary layer at any x location. So u at delta y is equal to 0.99 times u infinite. Okay, so that's the 99% of energy transport is already accounted for. So that's what is called the boundary layer thickness. And then you have something called a fully developed regime. What's a fully developed regime? How can we identify what is fully developed regime? What does it mean? Yeah, must have been taught to you in fluid mechanics. No? Oh, I see. Okay. So what happens is, supposing this is the profile that you will see. Okay. Now at some location x1, let's say this is x1. Okay. At some location x1. Okay. Or let's say at any x greater than x1, you will see that the profile du by dx will become 0. Okay. Now what does it mean? It means that, so suppose I zoom up this flat plate here. Okay. So at some location, what happens is that you will have a velocity profile, but then the profile will be maintained so this arrow distance tells you what is the velocity of the fluid at that location, and so the intensity or the velocity of each of the fluid particles across y direction would actually be maintained if you actually go in any x direction. So which means that if let's say that the velocity profile is u of y, okay, so if I call this as u1 of y, that's the velocity profile at x1 direction, okay, x1 location, and let's say this is x2, then the velocity profile will continue to remain the same, okay, which means that the boundary layer thickness will remain the same after the location x1. So that's what this regime is, what is called as a fully developed regime. So the regime before is called developing regime, and after x1 is called the fully developed regime. Okay. So now the properties in this boundary layer is actually characterized by what is called the friction coefficient. Okay. So it's the friction which is causing these kind of velocity profiles. So it's characterized by friction coefficient. Cf is the symbol that's given for friction coefficient, and that's given by the shear stress at wall, okay, shear stress at y equal to 0 divided by infinity by 2. okay. So that is the friction coefficient, and so this characterizes the shear stress which is present at the interface between the flat plate and the fluid, okay. So that will be mu into du by dy at y equal to 0 divided by infinity by 2, okay. So that is the friction coefficient. Shear stress is given by viscosity multiplied by the velocity gradient, x component velocity gradient at y equal to 0, okay. So now similarly, very similar to the momentum bound layer, if we want to characterize heat and mass transport in the boundary layer, so note that at the near the interface of these two phases, it is the boundary layer which is controlling all the transport processes. So therefore there has to be something called thermal boundary layer very close to the interface. There will be a thermal boundary layer. So supposing if the temperature of the flat plate is, let us say, Ts, okay, and the temperature of the free stream fluid is T infinity, okay. Now there is going to be a boundary layer so that is the thermal boundary layer. If I assume that Ts is greater than T infinity, okay, what will be the temperature profile in the, yes, it will, okay. So T infinity is the temperature of the free stream fluid which is above the boundary layer, and so the temperature profile will be as the fluid particles which is close to this surface would actually quickly reach equilibrium with that flat plate, and the temperature of that will be very close to or equal to the temperature of the flat plate itself, and therefore there will be a gradual decrease in the temperature till the boundary layer. So that is the temperature profile that you would expect, and similarly you can draw this at different locations. So one could define thermal boundary layer thickness. So this height is called thermal boundary layer thickness, which is again a function of the x direction, and so this is defined as, is very similar to how the momentum boundary layer was defined. We said 99% velocity. Similarly here we can define Ts minus T by Ts minus T infinity should be equal to 0.99, okay. So note that here the temperature of the surface plays an important role. Unlike in the case of momentum boundary layer, the flat plate is not moving, so the velocity of that surface is 0, right. So here everything depends upon the temperature of the flat plate, and therefore everything has to be scaled with respect to the measurable quantities Ts minus T infinity. So note that the measurable quantity has already cropped in here, and we are going to see a lot more of these when we discuss all kinds of aspects of convection, okay. Alright, so now we need to, similar to friction coefficient, we need to define what is called the heat transport coefficient, okay. How do we find this? Can we make a comparison? So I said momentum, heat and mass transport, they are all similar processes. How do we get the friction coefficient? The shear stress divided by, what is rho u infinity by 2? Yeah, what is rho u square by 2? It's inertia, right? So it's shear stress divided by inertia. What should be the equivalent here? Flux divided by, okay. So the way to see that is, suppose I zoom the interface, okay. Okay, so this is my interface. So I have a fluid particles which is on top of that surface. Now I write an energy balance, okay, in the fluid phase at the interface, okay. So whatever heat that is actually transported from the flat plate to the fluid is transported via conduction, right. So we said that the velocity of these particles is 0. So essentially the transport is occurring because of conduction. So therefore the flux at that location, this is Newton's law of cooling, h into Ts minus T infinity should be equal to, what's the diffusive flux? What's the diffusive flux? Whatever flux of heat that leaves the surface and goes to the fluid should be equal to the amount of heat that is actually diffusing at that location, right. What is that? Be careful, minus k into, sign is very important here, okay, minus k into dt by dy at y equal to 0. That's if you assume that there are things are not moving, right, because now it's a two-dimensional problem where there are gradients of temperature in both directions. So it's not just that it's simply being heating the fluid, but the fluid is also moving, so it's also convected. So it's not only leading to just heating the fluid and increasing the temperature, unlike what we considered for a case of a solid where it is pure conduction. Here the fluid is also moving. So therefore in the fluid stream there is a temperature gradient in both directions. So you can't assume that whatever fluid heat that is being transported is simply being used for heating up the fluid. That's not a correct assumption, because there is also a convection which is playing a role here. It's not pure increase in the capacity of the fluid. So therefore the local flux h into Ts minus, this balance is only at the boundary where the velocity is 0, only at the interface. At the interface the velocity is 0. We are able to do this simply because of the observation that there is no slip between the particles which is sitting right at the interface of the solid and the fluid. So we are not neglecting convection. Note that I said it's y equal to 0, right. So I am not neglecting convection here. I am only saying that the particles are at rest, therefore convection is not playing any role here, okay. So therefore correct, because of the pumping of the fluid there is a bulk motion, and that's actually leading to convective mode of heat transport, and in fact that's leading to the temperature gradient, okay. So therefore from here heat transport coefficient can be written as Kf. So note that this is the conductivity of the fluid, not the solid, okay. We are looking at heat transport from the solid at the boundary, and it is carried because of diffusion in the fluid phase at the interface. So this is diffusive flux at the interface. So note that it is very important to appreciate this. So this is the diffusive flux in the fluid phase at the interface. Yeah, if I write a balance for the flux inside the solid, that is correct, because you will say minus k solid dt by dy should be equal to the heat transport coefficient times the temperature gradient, right. But that is if you assume that it's not uniform. So I know how to maintain a uniform temperature inside the flat plate, that doesn't arise. But if it is not uniform, yes, you should consider the gradients inside.
How could the flux be non-equal?
Flux are equal. This will be equal to minus k into dt by dy in the solid phase. It will be equal. The gradients will be different. Be careful. The conductivities are different. So the gradients will be different, but the flux will be equal. No. Gradients will not be equal, because these are completely different objects. If I said that, sorry. So gradients are not equal in two different phases because their properties are different. Their conductivities are different. So the gradients cannot be equal. If they are in contact with each other, their properties are different, and so the gradients cannot be equal. It will be the flux which will be equal, okay. So whatever is the difference in the conductivities will be offset by the gradient for the flux to be equal to each other. Okay? So therefore based on this heat balance at the interface, we can write the heat transport coefficient as Ts minus T infinity. Okay. So that's the definition for heat transport coefficient. So far we liberally used heat transport coefficient, but this is the correct way to find the heat transport coefficient. It's the conductivity of the fluid. Remember that it's the conductivity of the fluid and not conductivity of the solid. Okay. So it's the, we are equating the heat transport flux of heat that leaves the solid and goes into the fluid phase with the flux that is actually conducted by the fluid because of diffusion at the interface, because the velocity is 0. Okay. Oh sure, steady state doesn't mean that it's not flowing. You can have a steady velocity, right, where the fluids are moving at a same bulk velocity. So remember that even for a simple 1D slab, in a steady state you had a linear profile. The temperature is not constant. So steady state does not mean temperature is constant, it's the temperature profile which is constant. So therefore gradients are not necessarily 0 when it is a steady state. Of course there can be a system where gradient is 0, but that's not always the case. Okay, any other question? Okay, so one could actually make a parallel to mass transport in a similar fashion, where we define concentration boundary layer, So suppose I have a flat plate where concentration of some species is CAS and you have a bulk stream. The fluid velocity is u infinity and the concentration of the species is Ca infinity, and you have a concentration boundary. Okay, and the profiles are very similar. If I assume that CAS is greater than Ca infinity, so that's the kind of profile, concentration profile, that you would expect in the boundary layer. That's the kind of concentration profile. So you can immediately see that lot of things that we talk in heat transport are very similar, simply because the profile is similar, therefore the gradient is similar, and therefore the process itself is similar. So we can define boundary layer thickness, if I call it as delta C. So delta C is defined as that location where CAS minus CAS minus Ca infinity is 0.99. So same definition, nothing different. And if I write a mass balance at the interface, then I can define heat transport coefficient Hm as, what will be the equivalent? Yeah, what will be this expression? Diffusion, it's minus D, so that's the equimolar counter diffusion. So I said there are two species that is going and one of the species can be in excess. So it will be the equimolar counter diffusivity of AB multiplied by dCA by dy at y equal to 0 divided by CAS minus Ca infinity. Okay. So that's the definition for mass transport coefficient. So what the important message that we have learned today is that the heat transport and the mass transport processes are actually very similar if the transport is occurring across from one phase to another phase where one of the phases is moving, right. So there is convection in one of the phases, and so the heat transport and mass transport processes are very similar to each other. And in fact you will see when we write model equations in the next lecture, you will see that it will see that the model equations are actually very similar to each other, and therefore the characterization process also will be very similar. Okay.